Good morning, ma'am.
So is my screen visible?
Yes, ma'am.
So let's start with the last module of this course. So in this module, we'll be talking about the frequency domain analysis of any control system. Okay, so we have already talked about how to do the time domain analysis. So time domain analysis meant that we were analyzing the output of the control system with respect to time. So we were providing different test signals, or so you have a control system. We were providing different inputs to the control system. So those standard inputs were like the step, impulse, step, ramp, parabolic. So these were the standard test signals, like the time domain test signals, which we were providing as the input to the control system, and we were observing how the output of the control system was changing with respect to time, given those kinds of inputs. Okay, so when we were discussing about these standard test signals, so if you remember that we talked about something which is something called a sinusoidal signals, but at that point of time we told that this is generally used for studying frequency response of a system. So we'll see how these sinusoidal signals, test signals, they are used for studying the frequency domain response of a system. So basically in the time domain, what we do is that the signal is expressed as a function of time, and in the frequency domain, what we do is that we translate or we transform the time domain signals into the frequency domain. Okay, so the frequency domain, what happens in this frequency domain, it's like, so given a function, so whatever function or a signal is given to you, so it can be represented by its magnitude as well as its phase as a function of frequency. So instead of expressing the signal, or instead of describing the signal as a function of time, if you can express the signal properties as a function of frequency, that is frequency is omega, so then that is the representation of a system in a frequency domain. So generally from this time domain to frequency domain, this transformation, this is done by Fourier transform. And so this is the general expression for Fourier transform. So if you have a time domain signal xt, so you can transform it or represent it into the frequency domain simply by using this Fourier transform. And this Fourier transform is, you see that integral t equals to ranging from minus infinity to plus infinity xt e to the power minus j omega t dt. Okay. So if you observe this Fourier transform, so you can say that this expression looks similar to the Laplace transform also. Okay, so in Laplace transform, what we were doing, we were taking a time domain signal and we were transferring it, or we were transforming it into that S plane. Okay, so S plane was something, so the value of S was equals to sigma plus j omega, right? So this was the S plane where you had this sigma and there was another frequency component omega, right? And in case of a frequency domain, what we'll only have this component omega. Okay, so you can say that Fourier transform is basically similar, or it is equivalent to the Laplace transform, but it is evaluated along the imaginary axis. That means we are assuming that the value of sigma is equals to 0. In that condition, when sigma is equals to 0, at that condition, if you do the Laplace transform, that will be equivalent to the Fourier transform. Okay, and this Fourier transform, the property of Fourier transform is that it cannot be used. So since the value of sigma is equals to 0, we have considered. So the property of Fourier transform is that it cannot be used to analyze unstable systems. So if and only if your system is a stable system, in that case only you can apply this Fourier transform and you can find out the corresponding frequency domain representation of the system. Okay, so we can say that frequency domain, it contains information only about the steady state part of a system. Okay, so a response, we know that a response always has a transient part as well as the steady state part. Okay, so when we were talking about the time response, so we saw that we can do the time response analysis. We can do it for transient response also. We can do it for the steady state part also. But in the frequency domain, basically the definition goes like this, that it is only It is defined as the steady state response of a system to a sinusoidal input. That is known as the frequency response of a system. Okay, so that means in frequency domain, we are only interested in analyzing the steady state condition of the system. So if you have a sinusoidal transfer function and the system is a linear time invariant system, in that case you can analyze the system simply by substituting the value of s by j omega instead of substituting s by sigma plus j omega. In case of Laplace domain, we were substituting s by sigma plus j omega, but in case of frequency domain, we will substitute s is equals to j omega because we are considering that the value of sigma is equals to 0. Okay, so basically so if you have an arbitrary signal, so a random signal if you have, so what you can do is that using Fourier transform, you can separate it out, or you can express it as a summation of in sinusoidal frequency components. Okay, and each frequency component can be individually analyzed, and you can use the superposition to add everything up and then reconstruct the output signal. Okay, so you can say that basically a periodic signal can be represented as a sum of its frequency components. The frequency components, they are calculated by the Fourier series coefficients. Okay, so let's see an example. So let us say that if you have a sinusoidal signal of a fixed frequency. Okay, so this is a sinusoidal signal of 1 kilohertz frequency, right? So this is the time domain representation. So the x-axis is time and the y-axis is the amplitude, and the frequency of oscillation or the frequency of the sinusoidal signal is 1 kilohertz. So if you want to represent this time domain signal into the frequency domain, so what will happen is that on the x-axis we'll have frequency. Okay, so the frequency of this periodic signal is 1 kilohertz. So there is only corresponding to 1 kilohertz, we'll have that corresponding amplitude of, so whatever, if the amplitude of this signal, let's say, is A, so that means at 1 kilohertz, we'll have an amplitude of A in the frequency domain. Okay, and at all other frequencies, since this sinusoidal signal does not have any other component at other frequencies, so that means the other components will be equals to 0. Similarly, if you have a sinusoidal wave of 2 kilohertz, then you will have in the frequency domain, you will have only one, so it will be represented by a signal which of amplitude A at this 2 kilohertz, right? So this was the case when you have a purely sinusoidal signal. Okay, so what if you have a signal which is a random in nature, or which is so if you have a signal something like this. Okay, so what is happening here is that, so this signal is basically summation of, if you see this video, so if the red signal is basically summation of multiple sinusoidal signals, and this sinusoidal signals, each of the sinusoidal signal have different magnitude as well as different frequency. Okay, so what you can do is that you can say that I am decomposing this overall signal into, let's say, these 3 purely sinusoidal signal with varying frequency as well as varying amplitude. And depending on these 3, so corresponding to this sinusoid, you will have one frequency domain, one frequency domain representation. Corresponding to all the other frequencies also, you will have different response, or you will have the representation in the frequency domain. So you can say that the time domain representation of this signal, that is, which looks like this. So in the frequency domain, that will be, the representation will be given by something like this. So you will have multiple, so this overall signal will be expressed as a summation of multiple purely sinusoidal signals, and each of those sinusoidal signals will have different frequency as well as magnitude. Okay, so depending on the frequency and magnitude of each of the sinusoidal components, you will get the, you can draw the, or you can write the frequency domain representation. So coming to the definition of frequency response. So frequency response is known as the steady state response of a system to a sinusoidal input. Okay, so in frequency domain analysis, what we do is that we vary the frequency of the input signal. So if you have a sinusoid, so you change the value of omega, the frequency of the sinusoid, and we monitor the system response over that frequency range. Okay, so then why do we, so if anyway we are we want to analyze the system response. So why not use only the time domain analysis? Why do we need to do this frequency domain analysis? So this frequency domain analysis, basically the advantages are that this frequency response tests are very simple. Okay, they are very simple and the measurements are very accurate, and it can be done using, they are pretty simple. So in case of time domain analysis, we saw that we had to do lots of like Laplace transform, inverse Laplace transform, which was quite sometimes which was quite tedious. But in case if you do the analysis of the system using in the frequency domain, then the response or the analysis procedure becomes much more simpler, and the analysis can be done using very simple instruments like the sinusoidal signal generators and very precise measurement instruments. So, and also the other advantage of using using the time frequency domain analysis is that if you have a complicated system and you don't know what is the transfer function of that system, okay, so let's say the system that you have, that is acting as a black box to you, okay, so you want to find out what will be the transfer function of the system, okay, so in that case, so you can do it from the time response analysis. You can do you can apply different test signals, you can observe the corresponding output, and from the analysis of the output you can find out the transfer function. But that is a very complicated process. But using frequency domain analysis, the transfer functions of very complicated systems also can be determined experimentally and in a very faster way and a very easier method. Okay. And also using this, another advantage of using frequency response is that the system may be designed to minimize the effects of undesirable noise. So you can find out where the noise is and how you can how you can design your system in order to have reduced effect of the undesirable noise that is there in your system. So in general, to design a closed loop system, what we do is that we adjust the frequency response characteristics of the open loop transfer function according to the design criteria which is provided, and by appropriately designing the system, the frequency response, that is the design criteria is maybe it is provided in the transient response analysis. So let's say if you're in your system is provided and you have to, it is given that you have to design it for a certain damping constant and a certain omega n value. Okay, so in order to design your system to achieve those values of zeta and omega n, what we do is that we adjust the frequency response characteristics of the open loop system, and from that we can satisfy the given conditions, which are the time response or the transient response specifications. So in general, the correlation between the frequency response and the transient response, that is not a direct one. Not a direct one as in there is no direct, so it is sort of a, so you cannot really say that if you have a very higher order system, then that response or the correlation is indirect, except for like second order systems. For second order systems, the correlation between the frequency response characteristics or the frequency response specifications and the transient response specifications, they are quite simple, and we will see later on how those specifications are related to one another. Okay, so now let's take if you take a linear time invariant system. Okay, so let's say that linear time invariant system, the output of the system is ys and the input of the system is xs. So the transfer function is given by gs, right? So now if you have if you are providing a purely sinusoidal input, so let's say the sinusoidal input is x sine omega t. So that means that the value of y and the, let's say the output that you are getting is simply a phase shifted sinusoidal signal. Okay, so before moving forward, so let me tell you one more thing. So another property or very useful property of using sinusoidal signal is that if you apply a sinusoidal input to a system, any kind of system, the output is also a sinusoidal signal with the same frequency as the input signal, as input, but different frequency, different phase. Okay. So if you have a linear time invariant system, this is the property of an LTI system, that if you provide a sinusoidal input to an LTI system, then the output sinusoid will also have the same frequency as the input, but the only thing is that it will be a phase shifted signal. Okay, so then yt will be equals to y sine omega t plus phi. So the frequency of both the output and the input are same, that is omega, and there is this phase change phi. So you can write that and now if you, from this equation, if you substitute the value of s, so let us substitute s with j omega. So you can write y of j omega divided by x of j omega will be equals to g of j omega, right? So this equation. So similarly, you can write y will be equals to x of j omega multiplied by the magnitude, or if you want to express in the magnitude form, so you can write y of j omega by x of j omega will be equals to g of j omega, correct? And from here, so since this is a complex quantity, so that means it will have a magnitude, it will have a phase, so there will be two components. Okay, so you can write for the magnitude, you can write y is equals to x magnitude of g of j omega, and if you just see the value of and the phase phi will be equals to the angle of g of j omega. Since this one, the input has zero phase, so phi here is equals to 0. So the output phase angle phi will be nothing but the phase angle of this transfer function. So that will be equals to tan inverse of the imaginary component of g of j omega divided by the real part of g of j omega. Right. So similarly, you can, if you want to express the magnitude of the transfer function, so you can write the magnitude of the transfer function will be the ratio of the magnitudes of the output sinusoid to the input sinusoid. Okay. So magnitude of transfer function is the amplitude ratio of the output sinusoid to the input sinusoid, and the angle of the phase angle of the transfer function will be equals to the phase shift of the output sinusoid with respect to the input sinusoid. That is the phase angle between, or the phase difference between the output sinusoid, that is given by yj omega, and the phase angle of the input sinusoid, that is given by angle of x of j omega. So this is the expression that we have. So we can write that, and this g of j omega, this is known as the sinusoidal transfer function. Okay. So sinusoidal transfer function is a complex quantity, and it is represented by a magnitude and phase angle with the varying parameter or the dependent parameter as the frequency. So g of j omega, you can write g of j omega is equals to magnitude of g of j omega and angle of g of j omega. So you can represent any sinusoidal transfer function as a magnitude component and a phase component. Okay. So if the phase angle that you are getting, that is a positive phase angle, then we say that is known as phase lead, and if you have a negative phase angle, that is known as phase lag. So in general, let's say that if you have, let's now consider a single loop feedback system. Okay, so in a feedback system, so if you have your feedback system looks like this, so you have G over here, you have H is your feedback, so this is C and this is R. So if this is the kind of a feedback, negative feedback system loop that you have, this is plus, this is minus, so you can write the expression for CS by RS. So CS by RS will be G by 1 plus GH, right? So now let's say that this value C by R, that is given by, that is equal to M of S. Now if you transform this into the frequency domain, so we'll just substitute S with J omega, and simply we'll get M of J omega will be equals to GJ omega by 1 plus GJ omega HJ omega, right? And this expression you can divide this expression, or you can simplify this expression and write it in terms of real part of mj omega plus imaginary plus j into imaginary part of this mj omega. Since this is a complex quantity, so it can be expressed as a summation of a real part plus j into summation of the j into the imaginary part, right? So mj omega is given by this expression. Similarly, it can also be expressed in terms of magnitude and phase, right? So the magnitude of mj omega is given by m omega, and the phase angle is given by, let's say, phi m of omega. And here you see both the magnitude and the phase, they are dependent on the frequency They are frequency dependent components. Okay. And this value of the magnitude m omega, that will be given by the magnitude of this one. So magnitude of gj omega divided by 1 plus gh j omega. This will give you m of omega, and similarly the phase will be given by phase of this numerator minus the phase of the denominator part, which is given by this. Okay, so m omega is basically, it is defined as the, or it is defined as the magnitude or the magnification of the feedback control system. Okay, so or you can say that this is equivalent to the gain or amplification of an electronic amplifier. Okay, so if you see the so ideally whenever we are talking about a control system, so the main purpose of the control system is that the output should follow the input, right? So this is R is my reference input or the set input that we are providing, and the main aim is that the output should follow this set input, right? So if your output has to follow this set input, so that means the value of C and R should be identical, right? So now if the value of Cj omega has to be identical to Rj omega, that means the output of the closed loop system follows the set input, then in that case you can write that this value of m of j omega, this should be equals to 1. In that case only Cj omega becomes equals to Rj omega, right? So that means for the design criteria or the for ideal design condition is that the value of mj omega should be equals to 1 at all frequencies. That means the magnitude of m omega should be equals to 1 irrespective of whatever frequency of the input signal that I am providing, right? So that means if you draw the frequency response of an ideal control system, so in that case the value of m of omega should be equals to 1, and it should keep on being equals to 1 till for any number of frequencies. So this should continue to infinity. Okay, but whenever we are dealing with a practical system, so what happens is that in a practical system, or you can say that rather the design criteria is that either it should have a flat gain for all frequencies, or at least it should have flat gain or gain of 1 for a specific range of frequencies. Okay, so let's say from 0 to omega c, in this range we want to operate the input to the system that ranges from the frequency range 0 to omega c. So then we would want our system to have a flat gain of 1 within this range, right? And the flat gain of 1, and correspondingly the phase response should also be a perfectly linear phase response in that frequency range. Okay, and in order to have this value of mj omega is equals to 1, so if you see from here, if mj omega has to be equals to 1, so that means the value of gj omega should be very large compared to 8j omega, right? If the value of gj omega is very large compared to 8j omega, you can simply ignore this component 8j omega and 1, and this will be equals to, this right hand side will be equals to 1. Okay. So this is the ideal condition, that gj omega should be very large, ideally infinite, which is practically not possible obviously, and the value of h of j omega should be a non-zero finite value. Okay. But so these are for the ideal conditions. Okay, but the moment you go to a practical system, obviously you will not have such a flat gain. So what we'll have is that we will have a gain which varies something like this. So it starts from 1, and then maybe it goes to some value, it reaches a peak, and then slowly it comes down. So this is for the practical. This is how the frequency response of a system looks like in a practical case. Okay, so then we will see like what all are these, what does the value of MP and all these things signify, that we'll see in some time. Okay, so this was the basics of the frequency response. So there are like 3 types of representations of the frequency response of a system. So the first one is the Bode diagram or the logarithmic plot. Then we have polar plot or the Nyquist plot, and the third one is the log magnitude versus phase plot or known as Nichols plot. Okay, so first we'll talk about Bode diagram or Bode plot. Okay, so now let's say that if you have a transfer function TF, so transfer function is given by G of j omega. Okay, so you can express this G of j omega as the magnitude of G of j omega multiplied by the phase component. So the phase can be expressed by e to the power j into phi omega. Okay, so if you take the natural logarithm, that is ln of both the sides, so on the left hand side you will have ln of g j omega will be equals to ln of this magnitude part plus ln of this component, and ln of this component is nothing but j into phi of omega, right? So you have a real part and you have an imaginary part. So the real part of the natural logarithm, that is the magnitude of this. You can say that this represents the magnitude of this transfer function, and the unit is given by Napier, and the phase imaginary part that corresponds to the phase characteristics of the transfer function. Now, instead of taking natural logarithm, if you take only log, so only log, what will happen is that, so this one will be replaced by log of gj omega plus log of e to the power j phi omega. So you will have this term 0.434 j into phi of omega. So the standard procedure in order to plot a frequency response or the frequency response of any transfer function or a system. So the standard procedure is to plot the value of 20 log magnitude of gj omega and the phase angle, that is phi omega, versus log of omega. So that means the x-axis, we take the x-axis as log of omega, or we represent omega in a logarithmic scale. Okay, and the y-axis is either 20 log modulus of gj omega, this is for the magnitude plot, and phi of omega, which is the phase plot. So in a Bode diagram, we have two plots. So one corresponds to the magnitude plot and the other corresponds to the frequency, corresponds to the phase plot. Okay, and in Bode diagrams, generally the frequency ratios, they are expressed in octaves. So in either in octaves or decades. So octave means if the frequency band is ranging from omega 1 to twice 2 of omega 1, then that is known as 1 octave. So 1 octave means frequency varying from omega 1 to 2 omega 1, and 1 decade means the frequency range between omega 1 to 10 times of omega 1. So that means 1 decade. So 10 times it is increasing. Okay, so we have already told that the Bode plot, basically it has so any sinusoidal transfer function. So this sinusoidal transfer function is nothing but g of j omega. So g of j omega can be represented by two plots. So one is the magnitude versus frequency, other one is the phase angle versus frequency. And the Bode plot is nothing but the logarithm of the magnitude of the sinusoidal transfer function versus frequency and the phase angle of the sinusoidal transfer function versus frequency. And both of these are plotted in a logarithmic scale. Okay. And the unit of the magnitude plot, in the magnitude plot we are doing 20 log g of j omega, and the unit of this is known as decibel, or in short we write it as dB. Okay. So the main advantage of drawing this frequency response of an open loop transfer function, the main advantage is that the multiplication of magnitude, that can be simply converted into addition. Since we are now dealing with the logarithmic scale, so we know that in log scale, if you have multiplication of different terms, so in log scale what happens is that we simply add the logarithm of each of the components. So this is like if you have a and b, so and if you transfer it into the log scale, so log of ab will be nothing but log a plus log b, right? So this is the property which will be utilized later on when we analyze different Bode diagrams. Okay, so this Bode plot, basically it provides you with a simple method of sketching a rough or an approximate log magnitude curve using asymptotic approximations. Okay, so the magnitude plot can be easily drawn using asymptotic approximations, but the phase plot, that can also be drawn easily if you have a template for certain functions. Okay, so if you have the template of, let's say, how the phase plot looks like for 1 plus j omega, if the value of gs is equals to 1 plus j omega, then how the phase plot looks like. So if you have that template with you, from that template you can easily find out what would be the phase curve for different other transfer functions as well. Okay, and the other advantage of using Bode plot is that since we are using logarithmic scale, so in logarithmic scale what happens is that the lower frequency range that is usually expanded. So if you see a log, I don't know whether you have seen a semi-log graph paper. So in a semi-log graph paper, basically what happens is that, so let's say this is 10, if this is starting from 1, 10, this is 100, then this will be 1000. So what happens is that in the lower frequency range, you have, it will go like this, and in the higher frequency range, this will be, the points will be, so this is the, if this is 1, then this will be 2, then this will be 3, 4. So you see that the lower frequency range, that is basically expanded, and the higher frequency range, that is contracted, you can say. And why this is important? Because most of the cases, the important properties or the important characteristics of the system, they can be found out if you analyze the lower frequency, the response of the system in the lower frequency range. So now draw this Bode diagram. Okay, so what happens is that in Bode diagram also we will draw the Bode diagram of the open loop transfer function. Okay, so in general, so before I move into how to draw the Bode diagram, so this do you have any doubts till now? Any doubts till now?
No, ma'am.
Okay. So basically this Bode diagram, so there are this, if you know the basic 4 factors of a Bode diagram, okay, so let's say that if you have a transfer function, which is open loop transfer function, which is given by g j omega h of j omega, okay, so there can be 4 basic factors. So one is it can have a gain of k, it can have integral or derivative factors, so integral factor will be 1 by j omega and the derivative factor will be j omega. Then they can have first order factors. So first order factors can be 1 plus j omega t and only 1 plus j omega t and 1 by 1 plus j omega t, and there can be quadratic factors. So quadratic factors can be represented by 1 plus 2 zeta j omega by omega n plus j omega by omega n whole square to the power plus minus 1. Okay, so if you remember that the second order, generally the second order transfer function, the characteristic equation was written by 2 zeta omega n s plus omega n square is equals to 0, right? So this was present in the denominator of a second order transfer function. So here if you simply substitute the value of s as j omega, you will end up with a factor which looks like this. Okay. So what we'll do is that we have to draw the composite Bode diagram by utilizing the plots for the basic factors. So we'll see how the plots for these basic factors look like, and then you can simply add these or depending on the transfer function which is provided to you, you can simply add the corresponding Bode diagrams in the semi-log graph paper, and you will end up with the overall frequency response of the full system. Okay, so we have to draw the composite Bode diagram by utilizing the plots for these basic factors and then finally adding the individual graphs graphically, because we know that addition of logarithms, logarithm of gains, that is corresponding to the multiplication of gain. Okay, so now if you have only, let's try to analyze for this value gain only k. Okay, so if you have this, so gain k means, so you have, so I'm just writing gh of j omega. Okay, so this is equals to k. Okay, so now if you have, if the value of k is greater than 1, then so what we'll do is that, so that means the logarithm will be 20 log modulus of gh of j omega. So this will be the magnitude plot. So this is nothing but 20 log k, right? And since k is constant, this is also a constant value, right? So you can say that the Bode plot or the magnitude plot for a gain k, that is given by a constant. In the magnitude plot, that is given by a constant, and the value of that constant is 20 log of k. So the log magnitude curve of a constant gain k is a horizontal straight line at the magnitude of 20 log k dv, right? So this x-axis is 20 log g of gh of j omega, that is given in dB, and the x-axis is the frequency, right? And obviously, so since this has only the real component, so the phase angle of this gh of j omega, when that is equals to k, the phase angle is equals to 0, right? So that means the phase angle is equals to 0. Okay, so you can say that from this one, so this is the open loop, this is the Bode diagram for our open loop transfer function, the transfer function being equals to gain k, right? So the effect of varying k in the system, it's like if you change the value of k, so that means depending on how you are changing the value of k, so this magnitude curve, it will either move up or it will move down. The phase angle will not change, obviously, because it will stay constant at 0. But if you change the value of k, the magnitude curve, that will either move up or it will move down depending on how the value of k is changing, right? So if you observe the magnitude curve for this gain, you can say that depending on how the curve is changing, you can say about how the gain of the overall system is also changing. So let's say if you have like if the gain is multiplied by is increased 10 times, so that means 20 log 10 into k will be nothing but 20 log k plus 20. So that means it is getting added or it is going up by a value of 20, right? Similarly, if you are multiplying the gain with a factor of 10 to the power n, so that can be written as 20 log k plus 20n, and 20 log k, also the property is it can be written as minus 20 of log 1 by k, right? So that was for the when the value of gh of j omega was equals to k. Okay, so now we have gh of j omega is equals to 1 by j omega or simply j omega. Okay, so let's first take the case of 1 by j omega. So the magnitude curve will be 20 log of magnitude of this 1 by j omega. So magnitude of this 1 by j omega is, since j omega is in the denominator, so it will be given by minus 20 log of omega, right? And the phase angle of this gh of j omega is the phase angle of 1 by j omega, which is nothing but minus 90 degree, since j is in the denominator and you don't have any other factor. So the phase angle is minus 90 degree. So you can say that for an integral factor, that is 1 by j omega, in that case the log magnitude curve, it is a straight line, and the slope of the straight line is given by minus 20 dB per decade. Okay, so this will be the slope. If you draw this minus 20 log omega with respect to omega, you will see that it is a straight line which is given by this, and the slope of this line is given by minus 20 dB per decade. Okay, and the phase angle, this is a constant phase angle at minus 90 degree. So why we are saying this 20 dB? So let's say that whenever if you are plotting the magnitude curve of a magnitude plot of a transfer function, you have to locate the 0 dB point. Okay, so the 0 dB point means the point at which the log magnitude curve is actually crossing your 0 dB, crossing the 0 dB line. So the 0 dB line is nothing but the frequency, the x-axis, right? So this x-axis, so that is known as the 0 dB line is here. So the x-axis is over here. So this is the 0 dB line. Okay, so that means it will be 0 dB when the value of omega is equals to 1, right? So at omega equals to 1, the value of this is equals to 0, right? So you can say that at omega equals to 1, 20 minus 20 log omega is equals to 0, right? Simply now if you see the value at omega equals to 0.1, then the log magnitude is equals to 20 dB. At omega equals to 10, you will have the magnitude is equals to minus 20 dB. At omega equals to 100, you have log magnitude, the magnitude is minus 40 dB. So you see that for every decade of increase, so from 0.1 to 1, from 1 to 10, from 10 to 100, so you see that the slope is actually getting increased by a value, or the slope is getting decreased by a value of 20 dB, which is happening per decade. So that's why we say that the slope of this curve is minus 20 dB per decade. So on a logarithmic scale of a semi-log graph paper, as I have already told, in the semi-log graph paper, you will have it will look something like this, and you will have this will be 0.2, this is 0.3, and slowly it will keep on coming closer to each other till you reach 1. Okay, in a semi-log graph paper, any frequency ratio is represented by the same horizontal distance. So that means that the distance between point omega equals to 1 to 10, that will be same as the distance between omega equals to 3 to 30, right? That is how a semi-log graph paper is generally designed. Okay. So in case of an integral factor, so the Bode plot looks like this. So you have the magnitude curve. So magnitude curve is a straight line with a slope of minus 20 dB per decade, and the phase curve is a constant one at minus 90 degree. Okay. So now if we consider the derivative term, okay. So for let's say that g of j, so gh of j omega is now equals to j omega, right? So we can simply find out the magnitude part. So 20 log magnitude of gh of j omega, that is magnitude of j omega, this is equals to 20 log omega, and the phase angle of j omega is equals to plus 90 degree. So we can draw that the Bode plot for this one is for this derivative factor is a straight line with a slope of plus 20 dB per decade, and the phase curve is a constant one at plus 90 degree. Okay. Now in order to draw this straight line, what we need to do is that we have to find out the 0 dB point. Okay. So the straight line, so the slope of 20 dB per decade, that can be anything, right? So this can also be a slope of 20 dB per decade. If I draw something like this, this is not parallel. So if I draw a line parallel to this, this is also this is also plus 20 dB per decade. Then how do we find out that which one is the actual curve? So for drawing that point, you need to find out the 0 dB point. Okay, so the point at which is the omega equals to 1 line. So at omega equals to 1, this point, this straight line should cross the 0 dB point. So the point which is crossing this 0 dB or the straight line which is crossing the 0 dB point at omega equals to 1, that will correspond to the log magnitude curve corresponding to this derivative factor j omega. Now if you have factors like 1 by j omega n. So 1 by j omega n means that, let's say that if you have poles of your system, you have multiple repeated poles in your system. So instead of having a single pole of 1 by s, let's say if you have 1 by s cube. So you have 3 poles at s equals to 0. In that case, what will happen? So you will simply have, so we will simply replace 1 by j omega with 1 by j omega to the power n, and that will be given by minus 20n log of omega. So, and minus 20n log of omega, that means that it will also be a straight line, but the slope of that straight line, that will no longer be 20 dB per decade, that will be equals to minus 20n dB per decade, and the phase angle will be equals to minus 90 degree multiplied by n. So you see that simply depending on how many poles or zeros are present in your system, according to that the slope of the Bode diagram will change. Okay. So similarly, if you have multiple zeros, so that means that if you have n number of zeros at s equals to 0, so that means j omega to the power n. So in that case, that is represented by a straight line whose slope is 20n dB per decade, and the phase angle is plus 90 degree multiplied by n. And all the magnitude curves should pass the 0 dB point at omega equals to 1. So this is the property which should be satisfied for drawing these curves. Okay. So this was about the integral and the derivative factors. So next we'll look like how the first order factor, if you have a factor like 1 by 1 plus j omega t. So similarly for 1 plus 1 by j omega t, if you just write the magnitude, so the magnitude of this part is equals to root over of minus root over of 1 plus, so 1 by root over of 1 plus omega square t square. So if you take it to the numerator, you will have the minus sign outside. So this is, so the magnitude is 20 log of this one is equals to minus 20 log square root of 1 plus omega square t square. Okay. So now here you see that if the frequency omega of your system that is much less than this value of 1 by t, so that means if omega t is much less than 1, in that case you can represent this as, you can ignore this term and you can write that the right hand side will be equals to nothing but minus 20 log of 1. So minus 20 log of 1 is equals to 0 dB, right? So you can say that for this particular first order factor, the log magnitude curve at low frequencies, that is till omega equals to 1 by t, that is a constant 0 dB line. Okay, and after omega becomes greater than omega, when omega is greater than 1 by t, that means at higher frequencies. So sorry, at higher frequencies what we can do is that we can ignore this term 1 and we'll end up with, so this can be approximated as minus 20 log of omega t. So square root of omega square t square, so it will be minus 20 log of omega t dB, right? And at the value of, so that means if you draw the plot, so let's say if this is your omega equals to 1 by t, this is your plotting in dB, this is your frequency. Okay, so at this point, till this point, the value, it was a straight line. So this was, let's say this is 0 dB. So this was a straight line at 0 dB, and after omega equals to 1 by t, so it started decreasing. So this will look like this. So this is a plot with minus 20 dB per decade. So here also, so you can simply find out the value of, you place different values. So at omega equals to 1 by t, so these are like or omega equals to 1 by t, I'll come later on. So at omega equals to 10 by t, so this is minus 20 dB. At omega equals to 100 by t, the magnitude is minus 40 dB. So that means for every decade, this is reducing by minus 20. So that means the slope is minus 20 dB per decade. So these two straight lines, this one straight line and this is the other straight line. So these two straight lines are known as the asymptotic line segments, and from these asymptotic line segments you can draw the approximate Bode diagram or the approximate frequency response of a system. Now at omega equals to 1 by t, what is happening? At omega equals to 1 by t, so you can simply substitute these values and you will get the actual value of the log magnitude curve at omega equals to 1 by t is given by minus 3. So but here if you simply draw the two asymptotes, you see that the two asymptotes, they are intersecting at 0 dB, right? But the actual value is minus 3 dB. So if you want to draw the actual value, so or the actual plot, so the actual plot will look something like this. So at here you will have minus 3. At omega equals to 1 by t, the magnitude will be minus 3 dB, and the red plot would be the actual Bode plot, but we can also approximate it using these line segments like this asymptotes. Okay, so we can say that for omega greater than 1 by t, this log magnitude curve is a straight line with a slope of minus 20 dB per decade, right? So now, okay, so again you can see, we can say that the logarithmic representation of the frequency response, it can be approximated by two straight line asymptotes. So one straight line asymptote is at 0 dB slope for the lower frequency range, that is from 0 to 1 by t, and the other straight line asymptote is a straight line with a slope of minus 20 dB per decade. Okay, and that is valid for the frequency range of 1 by t to infinity. Okay, and the frequency at which the two asymptotes meet, that is at omega equals to 1 by t, this is known as the corner frequency or the break frequency. And the other significance of this corner frequency or the break frequency is that this is basically the place at which the poles and the zeros of your system is. So if you have a factor of 1 by 1 plus j omega t, right? So that means from here you can say that there is a pole which exists at s equals to 1 by t, right? So that means this corner frequency that is given by, the corner frequency is equivalent to the pole or the zero that is present in your system, right? So for 1 by j omega t, so if your factor is 1 by 1 plus j omega t, then the corner frequency is equals to omega equals to 1 by t, and the exact phase angle plot, what you can do is that the exact phase angle plot can be found out by for different frequencies, like for lower frequencies, when you have omega equals to 0, the value of phi will be equals to 0. So simply find the phase part of this 1 by 1 plus j omega t. So at omega equals to 0, the value of phi is equals to 0. At omega equals to infinity, phi is equals to minus 90. So that means the phase curve will vary between, or will range between 0 degree to minus 90 degree. And at this corner frequency, the value of this frequency of this phase is minus 45 degree. So we know this point, and this third point. So we can draw an approximate curve, or you can find out a few points in between 0 to 1 by t and 1 by t to infinity. You can find out a few points, and you can draw the actual phase response characteristics, or the phase plot of the Bode diagram. Okay, so now, or you can say that the phase angle is basically skew symmetry about the inflection point, and the inflection point is this point, that is theta equals to phi equals to minus 45 degree. This is called as the inflection point. So about this point, so this is symmetric. The phase graph is symmetric about this inflection point. Sorry. So if you draw the this will be the approximate curve, and this is the exact curve. So if you draw the error between the approximate approximate magnitude curve and the actual magnitude curve, you will see that the error curve looks something like this. So the error is maximum at the corner frequency, and the maximum error is minus 3 dB. And slowly, as you move away from the corner frequency, the error in the approximation, error between the approximated curve and the exact curve, that reduces, and it becomes equals to 0. Okay. So similarly, for this for the factor 1 plus j omega t also, you can find out the values. You can draw the Bode diagram, and the advantage of Bode diagram is that if you have reciprocal factors, the log magnitude and the phase angle, that simply changes the sign. Okay, so we don't have to calculate again for reciprocal factors. For the factor of 1 plus j omega t, so the Bode diagram of 1 plus j omega t, that with the magnitude and the phase angles will be just the reverse or the minus sign of the previous one. So in the previous case, we had the magnitude was equals to minus 20 log square root of 1 plus omega square t square. So if now the value of gj omega, or the open loop transfer function, is 1 plus j omega t, so then this will become plus 20 log of under root of 1 plus omega square t square. Okay, so this will be simply 20 log 1 plus j omega t will be equals to minus 20 log of the reciprocal factor. Similarly, the same thing holds true for the phase curve also. And in both the cases, the corner frequency remains the same. The value of omega is equals to 1 by t. So, and in this case, what happens is that if you draw the Bode diagram, you see that in the lower frequency range, it is still a 0 dB line, and at the higher frequency range, it is a straight line with a slope of plus 20 dB per decade. In case of when the factor was 1 by 1 plus j omega t, this slope was in the downward direction, that was minus 20 dB per decade. And in case if you have a 0 in your system, which is in this order 1 plus j omega t, then corresponding to that 0, you will have an asymptote which is increasing with a slope of plus 20 dB per decade. And similarly, the phase angle will vary between 0 and 90 degree, right? And also, if you have multiple factors, like if you have 1 plus j omega t minus plus n, then the slope will be nothing but minus 20 into n dB per decade, or plus 20 n dB per decade, depending on what kind of, how many poles and zeros you have at that particular point. And similarly, the phase angle will also be n times of that at each frequency. Now, if you have quadratic factors, okay. So in case of quadratic factors, so this is given by something like this. So the quadratic factor is 1 plus 2 zeta multiplied by j omega by omega n plus j omega by omega n whole square. Okay. So now, if the value of zeta is greater than 1, then this quadratic factor, it can be expressed as a product of two first order factors with real poles. Okay, and if the value of zeta is less than 1, or the value of zeta lies between 0 and 1, then this quadratic factor can be expressed as a product of two complex conjugate factors. Okay, so the but only disadvantage for the quadratic factors is that this asymptotic approximation, that is the approximation by using straight line asymptotes, that is not very accurate if we are dealing with very low values of zeta. Okay, because at very low values of zeta, both the magnitude and the phase, they depend on the corner frequency. That is, the corner frequency here will be equals to omega n. So corner frequency is omega n and the value of zeta. So since both of these factors depend on omega n and zeta, so in that case, the approximation is not very accurate one for low values of zeta. Okay, so now if you write the log magnitude, so first write the magnitude, so 20 log of this factor, right? So this is nothing but 20. That can be expressed by this. So you simply find out what is the magnitude of this factor. Okay, so if the value of omega is much less than omega n, so that means that this factor can be, so these factors can, the omega by omega n factor can be neglected, and we can write that this is equals to minus 20 log 1. So that is equals to 0 dB. So that means that in this case also the low frequency asymptote is a horizontal line at 0 dB. And at high frequency, that is at omega greater than omega n, what happens is that the log magnitude becomes, so this 1 can be ignored. Okay, so what we can have is that we can, if we are dealing with approximately, so we can approximate this expression as minus 20 log omega square by omega n square, which can be written as minus 40 log omega by omega n dB, right? So that means that the higher frequency asymptote, that is a straight line with a slope of minus 40 dB per decade. So unlike the previous cases when we had a first order factor, in the first order factor, the slope of the asymptote was either plus 20 dB per decade or minus 20 dB per decade. But the moment we have a quadratic factor, so we have a second order factor, the slope increases by, or the slope is doubled. So that means we get minus 40 dB per decade for an integral factor. So if you have the quadratic factor in the denominator, if you have complex conjugate poles, so in that case, if we will have minus 40 dB per decade slope, and if you have a complex conjugate 0, then we'll have a slope, straight line of a slope of plus 40 dB per decade. So now these two asymptotes, so this low frequency asymptote, that is at 0 dB. So this low frequency asymptote, so this is, let's say 0 dB at low frequency. So this is, let's say this is omega n, this is dB. So at omega n, so this is 0 dB, and after omega n, so we have a slope, and this slope is minus 40 dB per decade. Okay. So now you see that this value, so whenever we are drawing these approximations, so this asymptotes, the asymptotes has been derived, they are independent of the value of zeta. But in the real, when you are drawing the exact Bode diagram, in that case the value of at omega equals to omega n, that is dependent on the value of this zeta. Okay, so the value of the magnitude plot at omega equals to omega n, that is at the corner frequency. So what happens is that if you see that these are the actual plots for finding out the response of open loop transfer function, which has a quadratic factor. So here you see, so this is my corner frequency. So this corner frequency is basically where omega by omega n is equals to 1. Okay, so these are the two asymptotes. So this was my one asymptote, and this was my other asymptote, which is moving like this. Okay, so now these two asymptotes are intersecting at omega equals to omega n. If you draw the exact Bode diagrams, then you will see that if you have smaller values of zeta, that is zeta equals to 0.1, 0.2, for those values of zeta, we see that we get a peak at omega equals to omega n, and this peak is known as the resonant peak. Okay, and if the value of zeta is becoming, when the value of zeta is less than 0.707, we'll see why this 0.707, why this particular value is coming. So for those values of zeta less than 0.7 or greater than 0.707, we do not get any such peak, and it is simply a smooth curve, and it follows something like this. So for the value of zeta, if the value of zeta lies between 0.707 to 0. Between this range, we get a resonant peak in the magnitude plot. Okay, so the magnitude of the error that in the approximation that can be done. So you see that for smaller value of zeta, this error is large. So that means that the approximation is not very accurate when you have very small values of zeta. And the phase angle, you can find out the phase angle phi will be equals to nothing but the angle of 1 by this factor. So this factor will be tan inverse of this, tan inverse of 2 zeta omega by omega n divided by 1 minus omega square by omega n square. So you can express this as a real part plus j of an imaginary part, and from there you can find out what would be the phase angle for that corresponding factor. Okay, so the phase angle will be tan inverse of the imaginary part by the real part. So here you see that the value of phi, that is dependent on both the value of zeta and omega n. Okay, so both zeta, so it depends on both zeta, omega n as well as omega. So when the value of omega is equals to 0, then the value of phi is obviously equals to 0, and omega equals to infinity, phi is equals to minus 180 degrees. So that means the phase plot will start from 0 degree and it will range from 0 degree to 90 degree, and at the corner frequency, that means at omega equals to omega n, the value of phi will be equals to minus 90 degree, and this value of phi, that is regardless of the value of zeta. Okay, at the corner frequency, irrespective of whether your zeta is a low zeta or a high zeta, you will have the phase angle as minus 90 degree. So this minus 90 degree is basically the inflection point in this case, and the phase angle curve that is symmetric or that is q symmetric about this inflection point, that is theta equals to minus 90 degree. Okay, so now if you draw or if you see the error or the error in dB versus the frequency for this asymptotic plot. So you see that as the value of zeta is decreasing, the error at the corner frequency. So this is the corner frequency, that is when omega, so this is omega. So U is basically defined as omega by omega n. So when omega by omega n is equals to 1, at that point of time, when you have very large values or very small values of zeta, then the error is quite large, and the error is less when we are dealing with a value of zeta which is around 0.707 or in that range. So now if you so now let's talk about the resonant peak which we just saw, which is happening when we are drawing the Bode diagram for a second order or a quadratic factor. Okay, so this is the quadratic factor that you have. So let's say g of j omega is given by 1 plus this. Okay, so we can write the magnitude of this plot. So magnitude will be 1 by square root of this term, right? And we have seen that g of j omega has a peak. So the frequency at which this peak is occurring, that is known as the resonant frequency, that is given by omega r. Okay, so from this figure you can understand that a peak will occur when, so that means a peak is occurring means the value of this g of j omega will be maximum. So peak means g of j omega will be maximum. So if g of j omega has to be maximum, so that means the denominator has to reach a minimum, right? And to reach a minimum, so what happens is that in order to find the minimum point, so that means that if you say that this part is given by g of omega, so this part should be minimum. So that means d of, if you do the derivative of this and equate it to 0, and then if you find out the value of corresponding omega, that omega will be given by this expression. Omega r is equals to omega n square root of 1 by 2 zeta, 1 minus 2 zeta square. And you see if the value of omega r, it has to be a real value. Obviously the frequency that we are talking about, that has to be a real frequency. So that means the value of omega r will be real if and only if the square root of 1 minus 2 zeta square, this is greater than 1, right? So that means 1 minus 2 zeta square should be greater than 1, and the value of zeta should be less than 0.707. So that is why this factor is coming. So the moment the value of zeta lies between 0 and 0.707. Only for those kind of cases you will get a resonant peak, and but after or beyond 0.707 there is no existence of any resonant peak. It will the response will simply follow a curve which look like this. So these are the cases where the value of zeta is greater than 0.707. So now simply, so this we have already told that for zeta greater than 0.707 there is no resonant peak, and the value of g of j omega, that the magnitude of g j omega, that decreases monotonically with increasing frequency. And the value of the resonant peak also you can find out. So the value of resonant peak, that is given by mr. So mr will be nothing but the magnitude of this g j omega at omega equals to omega r. So omega r we have already found out like this. So you can simply substitute those values here, and you will see that the value of mr, or the resonant peak, that is given by 1 minus 2 zeta under root of 1 minus 2 zeta square. An interesting thing over here is that you see that the value of this magnitude or this resonant peak, as well as this omega r, that is independent of the value of omega. Right, it is dependent only on the value of zeta and omega n, obviously the corner frequency. But these are all independent of any other frequencies. Okay. So now if you plot the value of this mr with respect to zeta, you will see that it will look something like this. Okay. So for zeta is equals to 0, then obviously the value of mr will be an infinite value, and after zeta equals to 0.707 there is no resonant peak. So that means the system will be, so if for zeta is equals to 0, that is for an undamped system, if an undamped system is excited at its natural frequency, then the magnitude of the transfer function, that becomes equals to infinite. So this thing we should always keep in mind, that is whenever, so we should never excite a system with an input whose frequency is equal to the natural frequency of the system. Okay, if you give an input such like that, then the magnitude of the transfer function, that will become infinite, and it will lead to an unstable system. Okay, and similarly you can find out the value of phi at, or the phase angle at this resonant peak, that is given by minus 90 degree plus sine inverse of zeta by under root of 1 minus zeta square. Okay, so till now we have seen that if you have like different, so we have seen that if you have a first order factor, how the Bode plot will look like. If you have a second order factor, how the Bode plot will look like. So obviously whenever you have a final or a complicated system will not have such simple factors. So it will have a combination of all different factors. Okay, so then how would you draw the Bode plot? Okay, so these are the general steps. So first of all, what you need to do is that whenever you are provided with a transfer function, in order to draw the Bode plot, first of all, you have to express the transfer function in this form. Okay, in this form means the numerator should be, or it should be in the form of, there should be a gain, there should be a first order factor, there should be factors for corresponding to integral or differentiator, depending on whether you have a pole or a zero in your system, and a quadratic factor also. If the quadratic factor is not there, then you will not have this. Okay, so once you have expressed the sinusoidal transfer function in this kind of a form, then the next step is that you have to find out, or you have to identify the corresponding corner frequencies which are associated with each factor. So for this factor k, only gain, there is no corner frequency. For this factor also there is no corner frequency. For the first order factor, for this factor the corner frequency will be equals to 1 by TA. For this factor the corner frequency is 1 by TB. Similarly, we have to find out what are the corner frequencies associated with each factor. And once we have identified that, then we will draw the asymptotic magnitude plot. So this plot basically consists of straight line segments with the slopes that will change at each corner frequency. So the moment, as we have already told, that the corner frequency means the frequency at which that is encountering a pole or a zero, and the property of the corner frequency is that the Bode plot, it undergoes a change in slope each time it hits a corner frequency. So either it will change the slope by, depending on what is the factor which is there, depending on that it will change a factor of plus 20 dB per decade if there is a zero at corner frequency, and it will change by a factor of minus 20 dB per decade if there is a pole at that corresponding corner frequency. Okay. Now if you have complex conjugate poles and zeros, then the slope will change by plus minus 40 dB per decade if you have a complex conjugate zero or pole combination. Okay. So next, so this will give you the asymptotic magnitude plot. So from the asymptotic magnitude plot, what you have to do is that you have to calculate the errors at taking certain frequencies, and from the errors you have to smoothen out the asymptotic curve and you have to draw the smooth curves, and the smooth curve will be the final or the exact Bode plot of the system. Okay. And similarly for the phase angle plot, you have to find the phase angle plot for each and individual all the factors and then add them up algebraically and in order to get the final phase plot. Okay, so let's try to do an example. Then this will be much more clearer to you. So let's say that here you have been given with a transfer function which is given by GS is equals to S into S plus 2, so on and so forth. Okay, so the first step is that we would express it in terms of, so this can be expressed as 4 into 1 plus S by 2 divided by, you have S 1 plus 2S, then you have 1 plus 0.05 S plus S square by 64. Okay, so it's simply instead of 1 plus S plus 2, you have to express it as 1 plus S into some factor. Okay, so from here you can write the value of G j omega. Okay, so G j omega will be simply substitute the value of this. So j omega by 2. Then in the denominator you have j omega, 1 plus 2 j omega and 1 plus 0.05 j omega minus omega square by 64. Okay. So we have expressed it in terms of this first order factor, second order factor, integral factor and all this. Okay. So then the next step is that you have to identify the corner frequencies. Okay. And we have to identify the factors of the transfer function in the order of occurrence in the frequency. Okay, so the corner frequency for this term is equals to, so if I keep on writing the corner frequencies, so let's say for the first term the corner frequency will be equals to 0.5. For this term the corner frequency will be equals to 2. Okay. Sorry, for this term the corner frequency is 0.5, for this term the corner frequency is equals to 2, and for this term the corner frequency you can find out omega 3 will be equals to 8. Okay, so omega 3 is basically equal to omega n, and this is nothing but you can simply write it as 1 plus 2 zeta j omega by omega n plus j omega by omega n whole square. So you can equate these two terms and you can find out the value of zeta. Zeta will come out to be 0.2 and omega n will be equals to 8. And the corner frequencies we know that for a quadratic factor the corner frequency is given by omega is equals to omega n. So that means omega 3 is equals to 8. So that means if you see in the frequency scale, so first we are encountering, so the first factor is the gain 4. Okay, or rather you can say that the first factor will be 4 by j omega. So the constant factors we will write, we will form an approximation, asymptotic approximation table. Okay, so in that table, so the first one is the constant, the first factor is the constant gain k, so the value of k is equals to 4. Then what you have a pole at origin, right? And that pole at origin is given by 1 by j omega, right? Okay, then you have a pole at s equals to minus 0.5, which is given by this. So this is given by 1 plus 2 j omega, right? So this is, so here you see that there is a pole at 1 plus at s equals to minus 0.5, right? Then fourth we have a 0 at s equals to 2, s equals to minus 2. Then you have a 0 at s equals to minus 2, and that is given by 1 plus j omega by 2. And we have a pair of complex conjugate poles. poles, and the value of zeta with the value of zeta is equals to 0.2 and omega n is equals to 8. Okay, so now we have, we already know how the asymptotic Bode plots looks for all these factors. Okay, so what we'll do is that, so for the first factor, let's say for j by 4 by j omega. So for this factor, there is no corner frequency. Okay, so the corner frequency is, there is no corner frequency, and the asymptotic plot will be, it will be a straight line with a slope of minus 20 dB per decade, right? The slope of minus 20 dB per decade is because of this 1 by j omega term, and this straight line should pass through the point. So the 0 dB point we need to find out, right? So the 0 dB point is the omega equals to 1, right? So the 0 dB point will be for 1 by j omega. If you have only 1 by j omega, then at omega equals to 1, it is crossing 0 dB, right? But now since we have 4 by j omega, so that means this straight line will pass at omega equals to 1. You will have the value will be equals to 20 log k or 20 log 4, which is equals to 12 dB, right? So if you, how we are finding out this? So you have, let's say if you write, so 20 log 4 by j omega, this would be the magnitude plot. Okay, so this is nothing but 20 log 4 minus 20 log omega, right? And at omega equals to 1, so at omega equals to 1, so this, if you calculate the whole thing at omega equals to 1, you see that this is 20 log 4 minus 20 log 1. This part is nothing but 0, so this is equals to 20 log 4. That means for this factor, the asymptotic line, it is crossing at the value at omega equals to 1 is equals to 20 log 4, that is equals to 12 dB. Okay, so this first two factors are done. So then we'll look into the second factor. Okay, so the pole. So now you have a pole, so 1 by 1 plus 2 j omega. So here the corner frequency is omega 1, that is equals to 0.5. Okay, so that means that till omega equals to omega 1, at till this point this is a 0 dB line, right? Or rather till omega equals to omega 1, this is a 0 dB line, and for omega greater than omega 1, you will have a straight line with a slope of minus 20 dB per decade, right? And similarly the phase angle, so for this one, this part, the phase angle was equals to minus 90 degree because this gain does not have any phase component, and for the denominator you will have minus 90 degree. And for this we will have the phase angle will vary from, so phi will vary from 0 to minus 90 degree, and at omega 1, so phi at omega 1 is equals to minus 45 degree. Now the next factor is 1 plus 0.05 j omega, right? So here the value of omega 2 is equals to 2. Okay, so this is also that for omega less than omega 2, this is a 0 dB line, and for omega greater than omega 2, so we will have a straight line with plus 20 dB per decade, straight line with plus 20 dB per decade slope. Okay. Last point is 1 plus j, the last factor is 1 plus this omega by 8 plus omega by 8 whole square, right? So here this is equals to 8, the corner frequency is equals to 8, the value of zeta is equals to 0.2. So that means for omega less than omega 3, this is a 0 dB line at low frequencies, and at higher frequencies you will have a line of minus 40 dB per decade. Okay, so once you have found out all these, so what we'll do is that we'll start drawing the Bode plot. Okay, so let's say that we start drawing the Bode plot. So we have this dB over here, and we have this. So this is, let's say, this is the frequency. Okay, so here what is happening is that, so first of all what we'll do is that we'll start with the factor of 4 by j omega. because this is the omega, the value of omega is over here. So we'll start with the lower frequency components. Okay, so for the first factor is omega equal, so this will be minus 20 dB per decade line, and at omega equals to 1, this is crossing 12 dB. Let's say omega, so this is omega equals to 1, some point, omega equals to 1, and so on and so forth. So on this plot, first of all, we'll plot all the corner frequencies. So we have a corner frequency at 0.5, 2, and 8. So let's say we have a corner frequency over here. So this is 0.5, another one is at 2 over here, and we have 8 over here. Okay, so this is omega 1, this is omega 2, and this is omega 3, and this is omega equals to 1. Okay, so the first straight line, so we will draw the first asymptote. So the first asymptote is basically crossing the, so if this is the 0 dB line, let us say, so this is 0 dB, right? So at omega equals to 1, the value of this straight line was equals to minus, so value of the straight line was equals to 12. So this is 12 dB, right? Here you see for this one, we'll have a straight line and which passes through 12 dB at omega equals to 1. Okay, so at omega equals to 1, so we'll have a straight line which looks like this. Okay, so it will keep on continuing. So this is a minus 20 dB per decade. So this is asymptote number 1, let's say. Okay, so now this will keep on continuing if we do not have the other factors, right? But this will keep on continuing till the point we hit the first corner frequency, which is omega equals to 0.5. So at omega equals to 0.5, what will happen is that since before till omega equals to 0.5, this factor has had 0 dB contribution. So this straight line will keep on continuing. But after omega equals to omega 1, this straight line has another slope gets added, another minus 20 dB per decade gets added. So this is 0.5 is here, right? So this is my asymptote 1. So it would have continued. So the straight line would have continued later on also, but before continuing, it has already hit the first corner frequency, and at this corner frequency there is a change in slope. So the change in slope means it will again have another, it will be added, another 20 dB per decade will be added. So the overall slope will become 40 dB per decade now. Okay, and it will keep on continuing till it hits the next corner frequency. So it will keep on continuing like this till it's come to the next corner frequency. So let's say this is asymptote number 2. Okay, so now it hits the second corner frequency, and at this omega equals to omega 2, omega 2 is equals to 2, we have another slope which is equals to plus 20 dB per decade. So this was minus 40 dB plus another 20 dB. So that means the slope will again reduce and it will become again equals to minus 20 dB per decade. Slope will occur over here. Okay, and it will keep on going till it hits again omega 3, and at omega 3 there will be a slope change of my addition of minus 40 dB per decade. So previously it was minus 20, now it is minus 20 plus of minus 40. So overall it will have a slope of minus 60 dB per decade. Okay, so every time we hit a corner frequency, there is a change in the slope. Okay, so what we have to do is that we have to simply add the two slopes and find out what would be the final slope of the curve. So this is the asymptotic approximation of the Bode plot for the given system. Okay, so in order to draw the actual one, so what you have to do is that you have to find out, you have to take a few frequencies before and after, and you have to smoothen the curve and draw the final Bode plot. Okay, similarly if you draw for the phase response, so for the first contribution, so let me draw the phase response in this plot only. So for the first part, for the factor 4 by j omega, it had a factor of only minus 90 degree. So let's say if this is minus 90 degree. Okay, minus 90 degree, this is minus 180 degree, and this is somewhere 0 degree. Okay, so for the first one, the slope would have been something like this, constant at minus 90 degrees. Okay, so for the second factor, which is 1 by 1 plus 2 j omega, so it varied between 0 and minus 90 degree. Okay, so it will vary between 0 and minus 90 degree, something like this. Okay, for the third factor, it will vary between 0 and plus 90 degree, right? So if you have plus 90 degree somewhere over here, so it will vary between 0 and plus 90 degree, right? And for the final factor, it will vary between 0 and minus 180. So it will change like this. So you have this is plot number 1. Sorry, let's say this is plot number 1. This is for 2. This is for 3, and this is for 4. So you have to simply add algebraically, you have to add all the phase angles at a particular frequency. So let's say at 0.5, you add all these phases, and you will get the actual phase for the given transfer function. Similarly, you can add all the frequencies and you will find out what would be the phase response curve for the given transfer function. Okay, so in a similar way, we can draw different other transfer functions also. So I'll give you some practice problems to solve. So the first step is that you have to express the equations in the given form. So that is form, like 1 plus j omega t, 1 plus j omega t1. In this form you have to express, and then you have to find out what all are the corner frequencies, and you have to arrange them in the order of occurrence. Okay, so depending on which pole is occurring or which zero depending on the occurrence of the pole and zero in the S plane, according to that you have to arrange the factors, and then at every corner frequency you have to see that what is the change in the frequency response or the change in the slope of the magnitude response that is happening. Okay, so once you can find out that, you can find out what would be the asymptotic plot, and from the asymptotic plot you can take a few points here on this side and that side of the corner frequency, and you can draw the smoothen out the final Bode diagram. Okay. So next we will talk about something which is known as all pass minimum phase and non-minimum phase systems. Okay, so basically an all pass system, it is basically if the system has a pole zero pattern which is antisymmetric about the imaginary axis. Antisymmetric about imaginary axis means that for every pole in the left hand side of a plane, there is a zero on the right hand side at the mirror image position. Okay, so that kind of a system is known as an all pass system. So if your transfer function is given by g of j omega equals to 1 minus j omega t divided by 1 plus j omega t. So that means it has a pole at minus 1 by t and so this is the pole, and it has a 0 at plus 1 by t, right? So that means the pole and zeros, they are antisymmetric with respect to the imaginary axis, right? It is with respect to the imaginary axis. So this kind of a transfer function, the systems which will have this kind of a transfer function, they are known as all pass system. And the property of this all pass system is that the magnitude of this g of j omega, that is always equals to 1, right? So the magnitude of so if you write the magnitude of g j omega, so this will be nothing but square root of 1 plus omega square t square divided by square root of 1 plus omega square t square. So irrespective of the value of omega and t, this would always be equals to 1. So this is a property of an all pass system, and the phase angle would be equals to minus 2 tan inverse of omega t, and the phase angle will range from 0 to minus 180 degree as the value of omega is increased from 0 to infinity. Okay, so this is an all pass system. So then we have something which is known as a minimum phase system. So a system is called minimum phase system if it has all the poles and zeros of the system, if they are lying on the left half of the S-plane, then we call it as a minimum phase system. And the property of this minimum phase system is that the transfer function of a minimum phase system, that can be uniquely determined from the magnitude curve only. We don't need to analyze the phase response curve in order to find out the overall transfer function of the system. Okay, and in case of a non-minimum phase system, what is happening is that some of the poles and zeros, they lie on the right half of the S-plane. So in that cases, the phase of that, the magnitude curve for both this minimum and the non-minimum phase systems will be same, but the magnitude curves will be different. Okay, so and the range of range of phase angle for a non-minimum phase transfer function, that is obviously greater than this minimum than the phase response for the phase range of the minimum phase system. So let's take an example. So let's say if you have this G1 is equals to 1 plus j omega t by 1 plus j omega t1, and G2 is equals to 1 minus j omega t by 1 plus j omega t1. Okay, so these two have same magnitude characteristics, but the phase characteristics are different. So this first one is basically a minimum phase system where both the poles and zeros are on the left hand side of the S-plane. But this G2 is a non-minimum phase system where you have a zero on the right hand side of the S-plane. If you draw the phase curve of, so if you draw the angle of G2 of j omega and angle of G1 of j omega, you will see that the range of G2 of j omega is the minimum one, G1 of j omega is the minimum one, and G2 of j omega is not the minimum among all these. Okay. So that means that the main difference between minimum and non-minimum phase system is that for a minimum phase phase system, the phase characteristics or the phase response is the minimum one, and you can find out the transfer function of a minimum phase system just by observing the magnitude plot of the Bode diagram. So if you have a system like G2 of j omega, which is given by this, so what we can do is that we can express it in terms of, we can add a term 1 plus j omega t here, and we can divide it over here. So this term, you see, this is nothing but an all pass system. This is an all pass system, and this, in this case, now you see that this system now have all the poles and zeros to the left half of the S-plane. So we can express a non-minimum phase system. We can sort of extract the minimum phase system from a non-minimum phase system just by adding, or we can by shifting each pole and zero one at a time from the right half S-plane to the left half of the S-plane. So this we have already told that so if a transfer function has multiple zeros on the right half of the S-plane, it is possible to extract them one at a time by associating them with all plus transfer functions, and each time an all plus transfer function is added, what is happening is that the phase lag is getting reduced until we reach a point where the phase lag is minimum. That means all the poles and zeros are lying on the left half of the S-plane. Okay, so now we'll see. So previously we have seen that if you have a transfer function is given to you, how you can draw the Bode plot from the transfer function. Okay, so now we'll see how to do the reverse one. Okay, so given a Bode plot, how you can estimate the transfer function of a system from the Bode plot. Okay. So as we already know that the magnitude curve, that is the gain in dB versus the frequency in logarithmic scale, that can be approximated by straight line asymptotes, and the slopes of the straight line asymptotes are given by plus minus 20 n dB per decade, depending on whether you have a positive, whether you have a pole or you have a single pole, you have a complex conjugate pole or zero, depending on what kind of poles and zero you have in your system. And the corner frequencies are the points at which the slope of the asymptote changes. So negative slope is for poles and positive slope is for the zeros. Now if you have a corner frequency and let's say the slope of the asymptote that is changing by 40 dB per decade. Okay, so now change of the slope by 40 dB per decade can mean two things. Okay, so one thing can be that there is a real, so either there is a double real pole or zero in the system, or there is a pair of complex conjugate poles or zero in your system. In either cases, the system will have a slope change of 40 dB per decade. Okay, so now this thing will be applicable only when we are dealing with a norm. So if such kind of a scenario exists, and if your system is a non-minimum phase system, then as we have already told that the magnitude curve is not sufficient to determine the exact transfer function. Okay, so in that case, the phase curve is also necessary. But whenever a transfer function is given to you, it is assumed that that is the transfer function of the minimum phase system. So that means from the plot, you can simply, from the Bode plot, you can simply find out, or from the magnitude part of the Bode plot, you can find out what would be the transfer function of a system. Okay. So now let's see, if you have a Bode diagram like this, an asymptotic plot of the Bode diagram is given by this. Okay. So here you see, so there is a slope change over here, and there is a slope, so there are like, so these three are the corner frequencies. So one corner frequency is 2.5, there is a slope change here. Then at omega 2 equals to 10, there is another slope change, and at omega 3 equals to 25, we have, so these are the three corner frequencies of my system. Okay, so this point is given as minus 12, and this is, so, and this is the 0 dB point. Okay, so if you want to find out the 0 dB point, so that means you have to extend it, right? And this is the 0 dB point, right? So we have to find out at what point this is crossing this line. Okay, this 0 dB point. Okay, so that means we can write that the change in magnitude in dB will be equals to slope of the straight line multiplied by the number of decades between the two frequencies, right? So now at this point, so this frequency is known, and this point, this frequency is known, so this is basically 1. Okay, so we can find out what will be the value at this point, right? So at omega equals to 1, we have to find out what is the value. Okay, so we can say that, so this is a slope of minus 20 dB per decade, so this is minus 20 dB multiplied by the number of decades between these two frequencies, so that would be nothing but log of 2.5 minus log of 1. Okay, so this is equals to minus 20 of log of 2.5, which is equals to minus 7.95 dB. Okay, so that means we can say that the magnitude will be equals to minus 12 minus of minus 7.95, that is equals to 4.05 minus 4.05. Okay, so that means this curve will basically imply that there is a gain. Otherwise, if there is no gain, then this point would have started from here. That is, it would have crossed 0 dB line at omega equals to 1. Since it is not doing that, so that means we will, so this slope that we will get, so we will have 20 log of k will be equals to minus 4.05, and from here you can find what is the value of k. K will be equals to 0.63. Okay, so here you see that at omega equals to 2.5, there is, the slope is equals to 0. The slope is equals to 0 means there is a, the slope change is from minus 20, there is a plus 20 dB per decade change. So at this point there is a plus 20 dB per decade change, and plus 20 dB per decade change will happen only if there is a 0 in your system. So if you try to write the transfer function of your system, so we have k, the value of k is 0.63 in your system. Then we have this curve will obviously signify that there is a pole at 0. So you have j omega in the denominator. Then here it signifies that you have a 0 at omega equals to 2.5. So that means you will have 1 plus. So let me write it in terms of s. So you have a pole at this point. So this is s, or a 0 at this point. So s by 2.5. Okay. So then at omega equals to 10, you have another plus. So here the contribution is another plus 20 dB per decade. So it was 0 till this point and another plus 20 dB per decade. So that means there is another 0 at this omega equals to 10. So that means that will contribute as 1 plus s by 10, right? And at omega 3 is equals to 25, it is becoming again 0. So that means there is a minus 20 dB per decade line over here. So that means minus 20 dB per decade will come from a pole, right? So the pole is located at 0.25 at 2.5. So this is 1 plus is by 25. So this is the approximate, or this is the transfer function from whose approximated Bode plot is given by this plot. So at every corner frequency, you can find out what is the change in the slope, and you have to find out that the change in that slope is because of what? Because of a pole, because of a zero, or what? So depending on whether it is because of a pole or a zero, depending on that, you will place those that pole or zero in the transfer function with the value that is at the corner frequency the pole and the zero is occurring. So this will be the position of the poles and zeros, and then you can write what would be the final transfer function of the system from the Bode plot. Okay. So any doubts? So what I'll do is that I'll stop today here, because I know it's been a long topic and it's been a long time. So we will discuss about the other things in tomorrow's class. So just go through the Bode plot basics, and in case if you find any difficulty in understanding, you can ask me in tomorrow's class and we'll discuss it then. Okay. So thank you everyone. We'll meet again tomorrow. Thanks.